So we're going to look at another definition, and this definition you're going to have memorized. It's the definition of our trig functions on a unit circle. Now, it says we have t being a real number, which is representing your angle, which you could look at it either as your angle or how far you are in this curved surface, which is your arc length. Either way, when you're on a unit circle, they're both the same. And we have a point x, y, so your x units over, y units up, and then once again, you can draw yourself a right triangle, always to the x-axis. So we can fill in this diagram. We can put t out here for our arc length or our angle. We're x units to the right, we're y units up because of our point, and your unit circle, so your radius is 1. Sine is referred to as your y value, because if you do your opposite of y over your hypotenuse of 1, you get y over 1, which is y. Cosine of your angle is adjacent of x over your hypotenuse, which is 1, so x over 1. Tangent is still y over x. It's y opposite over your adjacent. Then we still have those 3 reciprocal functions. So it's the same as the definition from the last section, section 2, except then we were doing it for any radius or hypotenuse. Here we're doing it with our radius of our angle being 1. And so all your r's become 1. So this is where we're going to be used to saying sine is equal to y, cosine is equal to x, but that's only when you are on a unit circle. Now, why does the sine of an angle plus a full revolution equal the sine of the angle, or vice versa for your cosine? And that's because your period of sine and cosine is 2 pi. Because if you go around your unit circle a full revolution, which is 2 pi, everything starts to repeat. So we have our unit circle here on the left, and we're going to look at graphing your angle compared to your y value, which is sine. So here at 0 radians, your y value is 0. So 0 radians, your y value is 0. At pi over 6, your y value is a half. So we go to pi over 6, we go up to 1/2. Here at pi over 4, your y value is root 2 over 2. So at pi over 4, you'd be at root 2 over 2. At an angle of root 3, so we lay out root 3 this way, or not root 3, pi over 3, our y value is here at root 3 over 2. Here at 90 degrees, which is our pi over 2 in radians, we're at a y value of 1 because it's a unit circle, you're 1 unit up. Then you start coming back down here. You'd be at 2 pi over 3, same height as your pi over 3. At 3 pi over 4, you're at the same height as you were for your pi over 4. Whoops, over here. And then we keep doing that and plotting these points all the way around your unit circle for all these different angles. And when you start connecting all these points, you get what's referred to as your sine graph. And so if you draw in a nice smooth curve, you get what you were seeing here of a smooth or of a sine graph. It's a nice smooth curve. And how far you go up here above your axes matches how far you do go down below your axes. How wide this part above is equal to how wide the part below is. So you got to be careful of that when you're graphing. So on the next slide here, we get to our sine graph that we just had. I'm not going to go ahead and redo it, but it's just what we were looking at. So our domain, what can we put into this? And here we're saying our angle is x, because we often let x be your input. You can look at any angle you want, so your domain's all real numbers. Your range only goes up to a height of 1 down to a depth of -1, so range is once again how far up and down you go. Your y-intercept is where you cross the y-axis, which is at 0. We have no vertical asymptotes because it's a continuous function. You can draw it without lifting up your pencil. Our x-intercepts are at 0. pi, 2 pi, then it would be 3 pi. So really any multiple of pi. And then our period is 2 pi. You have to go 2 pi before you start to repeat. Now, we would say your sine function is symmetrical about the origin. So if you take this, rotate it 180 degrees about the origin, you will get the rest of your sine curve over here, which means it is an odd function. So I would encourage you to do an accurate graph of your sine curve with your tick marks along here, with the appropriate height and appropriate depth, because you're going to be referring to all 6 of these trig graphs a lot. So I would encourage you to have an accurate graph of these for your notes. So now we'll go ahead and take a look at cosine. Now, cosine is looking at the x. Well, our x-coordinate at 0 is 1. Our x-coordinate here at pi over 6 is root 3 over 2. Our x-coordinate right here at pi over 4 is root 2 over 2. Our x-coordinate right here at pi over 3 is 1/2. Our x-coordinate at pi over 2 is 0. Our x-coordinate right here at 2 pi over 3, that is negative 1/2. Our x-coordinate here at 3 pi is negative root 2 over 2. Our x-coordinate here at 5 pi over 6 is negative root 3 over 2. Our x-coordinate here at pi is negative 1. And then we continue to plot all the x-coordinates all the way around your unit circle. And when you do that, you get this shape. So when we connect all of those, we end up getting what what's referred to as your cosine graph. Cosine and sine are really the same graph, but one of them is shifted a little bit horizontally compared to the other. But other than that, they're the same graph. So since they're the same graph, just shifted, your domain's going to be the same. Your range is how far up and down it goes, which is from 1 to negative 1. In this case, our y-intercept where we cross the y-axis is at 1. We have no vertical asymptotes. Our x-intercepts are at pi over 2 plus a pi to get to this one, which is 3 pi over 2, plus another pi, which would be 5 pi over 2. So we're going to say it's pi over 2 plus any pi, which is a half revolution. Your period is still 2 pi. Your cosine graph is symmetrical about the y-axis. So if you take this, fold it over the y-axis, you would get the rest of your cosine graph over there, which means it would be considered an even function. Now we'll look at your cosecant graph, which we know is the reciprocal of sine. So we have the sine graph drawn over here. And once again, on all these, do accurate graphs, do accurate sketches. So we're going to go ahead and do the reciprocal of this, which is 1. Reciprocal of 1 is 1. We come over here, we're at a height of a half. We do our reciprocal, we're right here. We do the reciprocal of something that's close to 0, like 1/10. That would be 10 over 1, which would be way up here. Or here, you're at a height of 1/2. That reciprocal is 2. Here, you'd be at a height of like 1/5. The reciprocal of that would be way up here at 5. Then we can do our reciprocals over here. The reciprocal of negative 1 is still negative 1. The reciprocal here of negative 1/2 would be negative 2. And then the reciprocal of something close to 0 is big, and so it would be a big negative. Here, we're at a height of negative 1/2. Do a reciprocal, we get negative 2, and then we'd be down here. So now we can go ahead and draw in that. We are going to have a horseshoe up, and we're going to have a horseshoe down. And then it really does continue on past that in each direction. But you need to have at least one full period. So because we have vertical asymptotes, and vertical asymptotes are where the denominator is 0, so wherever our sine is 0 is our vertical asymptotes, and sine was 0 at any multiple of pi. So your domain is really all real numbers except any multiple of pi. Your range is how far up and down it goes. Well, it comes from negative infinity, comes up to -1. Takes a break, starts at 1, and goes on forever. So less than -1, less than or equal to -1, and greater than or equal to -1. And I don't know why I didn't have the equal to in there. Sorry about that. So your x-intercepts, well, it never crosses the x-axis. Our period is still 2 pi because it's the reciprocal of sine, and the period of sine is 2 pi. Our sine was symmetrical about the origin, so its reciprocal is symmetrical about the origin, which means it is an odd function. Our y-intercept, well, you can see here our graph never crosses or touches the y-axis, so it does not apply. Now, your cosine, we're going to do pretty much the same. But remember, sine and cosine were the same graphs, just shifted sideways. So if we graph this, reciprocal of 1 is 1. Reciprocal of a half is 2. Reciprocal of a half is 2. Reciprocal of -1 is -1. Reciprocal of -1/2 is -2. Reciprocal of -1/2 is -2. And so you can probably now see that your graph ends up being the same as what we had before for your secant, just shifted over a little bit. And so this is your secant graph. So your secant and cosecant graphs are both horseshoe ups and horseshoe downs. We have vertical asymptotes, and your vertical asymptotes are at wherever your cosine is 0. This is where your cosine was 0. So therefore your domain is all real numbers except those spots. X-intercept, you can see that we're always either above or below. We never cross, so there are none. Your period of cosine, which we're dealing with the reciprocal of, is 2 pi, so its reciprocal function of secant has a period of 2 pi. Range is still going to be the same as it was before for our cosecant, and I got to switch that. And we can see that we do cross the y-axis here at a height of 1. Now remember, your cosine graph was symmetrical about the y-axis. So you could take what's over here, reflect it over the y-axis, and you get this shape over here, which means it's an even function. Then we're going to move on to tangent. Remember, tangent is y over x. So you got to take this y value divided by this x value. If you do that, you're going to get this shape. So as we just look here a little bit, we look at this point right here, you do your y over x for tangent, or sine over cosine, you get 0 over 1. So that's why we have this point here. At 45 degrees, or pi over 4, I should say, they're both root 2 over 2 and root 2 over 2. So when you divide them at pi over 4, you're going to be at a height of 1. As you try to get closer to here, to this, we know 1 divided by 0 is undefined. But if I go something close to 1 over something close to 0 for this point here, it would be close to 1 over something really small, which ends up being a big number, so that's why it ends up going up forever. And then down here, it would be the same thing, just all those negative values instead. Now, your tangent graph is this basic shape. We have vertical asymptotes at whatever causes the bottom to be 0, which is when your cosine is 0. So when you were dealing with your secant graph, which is when cosine is in the bottom, you have the same vertical asymptotes here. You do see that we cross the x-axis at 0, pi, 2 pi, so any multiple of pi. You can see with your tangent graph, you only have to go from negative pi over 2 to positive pi over 2, or a total of 1 full pi, before it starts to repeat itself over here. So your period is pi. Now, if you know where your asymptotes are, your domain is all real numbers except that. Your range, you can see you start here at 0, go up forever, also start at 0, go down forever, so it's all real numbers. And you can see you cross your y-axis at 0. Now, if you take your graph and reflect it about this point by rotating it at 180 degrees, you end up getting this to be rotated down here. So it means it is in symmetrical about the origin, which is an odd function. Then we'll go ahead and take a look at cotangent. Cotangent, all we have to do is do cosine over sine, or take our tangent graph we just had and do the reciprocal of all these y values. Either way, you get this cotangent graph in green with your asymptotes. Notice your asymptotes occur at whatever would cause the bottom to be a 0, which is when sine is 0. So your cotangent has the same vertical asymptotes as your cosecant graph, which was at any multiple of pi. So therefore your domain is all real numbers except those vertical asymptotes. You can see we cross at pi over 2, and then we're going to go a pi at 3 pi over 2, then add another pi to 5 pi over 2. So your x-intercepts are at pi over 2 plus any multiple of pi thereafter. Our period of cotangent is the same as tangent, which is pi. And it is symmetrical about the origin, which means it's an odd function. You can see we have a vertical asymptote on the y-axis, so we have no y-intercept. The range, you can see you start at 0, go up forever, start at 0, go down forever, so your range is all real numbers.